Take a look at this image. You've seen it 1,000 times in every classroom textbook. The nucleus sits in the middle, and little electrons spin around it like a miniature solar system. It looks simple. It feels right. But here is the problem. It is completely wrong. If atoms actually worked like this, you, me, and this entire planet would collapse and vanish in less than a billionth of a second. So what is actually holding reality together? The answer is far stranger and far more beautiful than a simple drawing could ever explain. Here is the problem with that solar system picture. It relies on gravity to explain how planets stay in orbit, and we assumed electricity worked the same way for atoms. A planet orbits the sun, and it keeps going because there is no friction in space to slow it down. It just coasts. But an electron is not a planet. It is a charged particle. And the old laws of physics, the ones we trusted for centuries, were very strict about charged particles. They said that if you take a charged particle and accelerate it, if you make it turn a corner or spin in a circle, it must radiate energy. It has to give off light. It is leaking energy just by moving in that circle. Think of it like a spinning top that is constantly losing its spin. As it loses energy, it slows down. It gets wobblier. It falls inward. So, and if the electron were truly orbiting the nucleus, like a little planet, it would be constantly radiating away its life force. It would spiral inward faster and faster. It wouldn't be a gentle drift. It would be a catastrophe. A death spiral. In a fraction of a second, every electron in every atom of your body would crash into the nucleus. There would be a flash of ultraviolet light, and then, poof, no more atoms, no more matter, no more you. According to every rule of classical physics, the universe should not exist for more than a heartbeat. But look at your hand. It's still there. The chair you are sitting on hasn't collapsed into a burst of light. The world is stable. The atoms are incredibly durable. They survive fire, they survive time, they survive collisions. So, the picture in the textbook isn't just a simplification. It is a lie. And the electron cannot be moving in a circle, and it cannot be a particle in the way you think of a particle. If it were, we wouldn't be here to talk about it. So, what is keeping it from crashing? To save the universe from collapsing, we had to give up the idea of the electron as a thing. It is not a little hard ball. It is not a marble rolling around a track. Stop imagining that. Instead, imagine a ceiling fan. When it is stopped, you see the blades. But turn it on, faster and faster, and the blades vanish. All you see is a blur, a shimmering disk. Now, here is the twist. The electron is not a tiny blade spinning insanely fast inside that blur. The electron is the blur. It is a cloud. It is a smear of probability wrapped completely around the nucleus. It's like a soap bubble trembling in the wind, or a bell that's been struck and is just sitting there, ringing. It's jiggling. It's wiggling. It's everywhere at once. If you try to pin it down, you might find it here or you might find it there. But before you look, and it isn't hiding in a specific spot, it is the entire cloud. And because it is a wave, because it is spread out, it doesn't lose energy and crash. It can't crash. A wave doesn't fall into the thing it surrounds. It just sits there, vibrating. This jiggle is what keeps the atom puffed up. It's what gives matter its size. But here's where it gets really strange. If the atom is just a tiny nucleus surrounded by a ghostly cloud of probability, that means it is almost entirely empty space, vastly empty. So, why don't you fall through your chair right now? Why can you walk on the floor without slipping through the cracks of reality? Go ahead, clap your hands. Smack. It feels solid, right? It feels like skin hitting skin. But that is an illusion. You have never actually touched anything in your entire life. What you felt was a force field. You see, electrons are very particular. They follow a strict traffic rule called the Pauli Exclusion Principle. It says that no two electrons can be in the same place, doing the same thing at the same time. They are incredibly stubborn. When you bring your hand close to the table, and the electron clouds in your hand and the electron clouds in the wood start to overlap, and they panic. They scream, "This is my spot, get out!" They push back with a ferocious force, not because they are hard objects bumping into each other, but because the laws of the universe forbid them from occupying the same state. That resistance, that refusal to merge, that is what you call solid. You're simply floating on a cushion of electric arguments. But hold on, because it gets even more uncomfortable. To make this whole system work, electrons possess a property called spin. And this is where your brain is going to struggle? Don't worry, it struggles for physicists too. We call it spin because the math looks exactly like a spinning top. But here is the paradox. An electron is a point particle. It has no size. It has a radius of 0. If you spin a basketball, the outside moves. But if you have a point with no surface, nothing can move. It physically cannot rotate. So, is it spinning? No. And yes, Richard Feynman famously said, "I think I can safely say that nobody understands quantum mechanics." This is exactly what he meant. The electron isn't physically turning in space. It just has spin. Think of it like a label, or a color, or a flavor. And it is a fundamental tag attached to the particle that tells the universe how it behaves. It doesn't need to rotate to have angular momentum. It was born with it. It is just a rule written into the code of reality. So, we have peeled away the electron shell. We know it's just a ghost cloud, but surely the center, the nucleus, is solid? That is where all the weight is, right? Protons and neutrons. The heavy stuff. Well, let's look inside a proton. Inside, you find 3 tiny specks called quarks. But if you put those 3 quarks on a scale, they weigh almost nothing. They account for maybe 1% of the proton's mass. 1%. So, where does the other 99% of you come from? It comes from the nothingness in between. The quarks are moving frantically, buzzing around at near the speed of light, held together by a force field called gluons. They are snapping and pulling like invisible rubber bands. And there is so much energy in that frantic motion, so much tension in those fields, and that, according to Einstein, that energy becomes mass. Think about what that means. You are not made of solid material. You are made of trapped energy. The heaviness you feel in your body is just the frantic buzzing of the vacuum trying to hold itself together. So, if the electron is a cloud and the nucleus is trapped energy, what is the universe actually made of? We have this habit of thinking of space as an empty box, a stage where the actors, the particles, enter, move around, and exit. But Feynman showed us that there are no actors. There is only the stage, and the stage itself is alive. Imagine a vast, calm lake extending to the ends of the universe. The water is perfectly still. This is what we call a field. Now, imagine you tap the surface. A ripple forms and travels across the water. If you were standing on the shore, you might point at that ripple and say, "Look, a thing, a particle." But we know better. There is no independent thing moving across the water. The water molecules aren't traveling from the center to the shore. They are just moving up and down. And the particle is just a disturbance in the field. This is the deepest truth of our reality. The universe is filled with these invisible fields. There is an electron field, a quark field, an electromagnetic field, everywhere, all the time. Right now, in the empty space between your eyes and this screen, these fields are there, quietly vibrating. When we say we have an electron, we just mean there is a little knot of energy, a little ripple, moving through the electron field. When it annihilates, the ripple settles down and the energy goes into another field. This changes everything. It means we are not separate entities isolated in a void. We are all made of the same fabric. We are just temporary waves rising and falling in the same infinite cosmic ocean. Let's bring this back to something you can see. Look at a massive tree, a giant oak standing in a field. Where did all that stuff come from? Where did the wood, the bark, the leaves? Where did all that mass come from? Most people think it came from the ground. They think the tree ate the dirt. But if you dig up a tree, there is no giant hole where the soil used to be. The ground is largely still there. So, did the tree come from nothing? No. It came from the air. This is the part that always stops me in my tracks. A tree is built almost entirely out of carbon dioxide. It breathes in the air, and it uses sunlight to do something incredible. The sunlight hits the carbon dioxide and says to the oxygen, "Get out of here, leave the carbon alone." It pushes the oxygen away, which is good for us because we breathe that, and it keeps the carbon, and it uses water as a kind of glue, sticks the carbon atoms together into long chains, and builds the trunk. A tree is literally solidified air and sunshine. Now take that wood and put it in a fireplace. Start a fire. What is happening? It is the exact reverse movie. The oxygen in the room sees the carbon in the wood and says, "I missed you." They rush together. They snap back into a tight embrace, and that snap releases energy. But what energy is that? It is the exact same energy the sun used to pull them apart 50 or 100 years ago. The light you see dancing in the flames? That is sunlight that was trapped in the structure of the wood for decades, now being released back into the room. The heat you feel on your face? That is the heat of a summer day from a century ago. You're not just burning wood. You are unlocking a battery made of air and sun. Now, I can hear a question bubbling up in the back of your mind. It is the same argument that happens in university hallways and comment sections every day. You might say, "Hold on. Are you telling me the world is made of math? Is an atom actually a wave function? Or is that just a model we use because we aren't smart enough to see the real gears turning underneath?" It is a fair question. It feels like a cheat, doesn't it? It feels like we are just making up numbers to fit the experiment. But here is the spooky part. These equations, this math that describes the cloud and the jiggle, it is not just a rough sketch. It is the most precise description of reality human beings have ever created. Think about it this way. If you used these equations to calculate the distance from New York to Los Angeles, and this math would get you there within the width of a single human hair, that is not just a lucky guess. That is not a useful fiction. If the math says the electron is a ghost, and the experiment agrees with the math to a dozen decimal places, then we have to be humble. We have to stop telling nature what she ought to look like billiard balls or solar systems, and start listening to what she is actually saying. And she is speaking in calculus. But there is one final ghost in the machine, one that is perhaps the most unsettling of all. We call it the measurement problem. You see, we said the electron is a wave, it is a cloud. It is jiggling everywhere. But when we actually take a picture of it, when we fire a photon at it to see where it is, we don't see a cloud. We see a dot, a tiny specific point. So, where was that point before we took the picture? Imagine you are in a completely dark room and you flip a coin. It hits the floor. You hear it land. Now, in the dark, is it heads or tails? In our normal world, it is definitely one or the other, and you just don't know which. But in the quantum world, it is not that simple. In the dark, the coin is effectively both. It is a mixture of heads and tails, a ghost coin hovering in a state of possibility. But the moment you turn on your flashlight, snap, the universe is forced to make a decision. The possibility wave collapses. It becomes heads. The act of looking created the reality of the outcome. This leads to a question that keeps physicists awake at night. If looking is what forces the universe to be solid, what happens when we aren't looking? Does the moon exist if no one is looking at it? Or does the universe save computing power by only rendering the physical world when an observer is there to see it? It starts to feel less like a rock-solid reality and more like a video game that only loads the room you are currently standing in. So, step back and look at the entire picture. It is a symphony played on a scale we can barely comprehend. At the very bottom, there are no things. There is just the ocean, the quantum fields, heaving and vibrating in the dark. Out of this ocean, little knots of energy rise up. We call them particles, but they are really just persistent waves, frantic and wild. They want to crash. They want to merge. But the rules of the game, the Pauli Exclusion Principle, the specific charge of the electron, the speed of light, they step in like a cosmic architect. They force these wild waves to stack up. They force them to keep their distance. They turn the chaos of the quantum world into the structure of the periodic table. Because they are forced to stand apart, they can snap together. Atoms link to form molecules. Molecules link to form proteins, and proteins fold to build cells. And cells come together to build you. This is the miracle. You are a universe of jiggling, uncertain, probability cloud ghosts. You are 99.99% empty space. You are made of energy that shouldn't be stable, ruled by math that defies common sense. Yet, here you are, solid, stable, conscious. We are walking, talking miracles, balanced perfectly on top of a storm of invisible fields. The chaos down there creates the order up here. But I want to leave you with one final mystery, a splinter in your mind. We know the rules now. We know about the spin, the fields, and the exclusion principle. But we have absolutely no idea why the rules are set exactly this way. If the electron were just a tiny bit heavier, or if the electromagnetic force were just a fraction weaker, none of this would work. The stars wouldn't ignite. The carbon wouldn't form. The universe would be nothing but a cold, dark, shapeless soup. It feels suspicious, doesn't it? It feels like the dials of reality were tuned with impossible precision just to allow you to exist. Feynman once said that doing physics is like watching a great game of chess played by the gods. We watch the board. We eventually learn the moves. We understand how the bishop slides and how the knight jumps. But we still don't know the strategy. We don't know the ultimate objective. And most haunting of all, we have no idea who set up the board in the first place. I'll leave you to imagine who might be sitting on the other side.